So Bismillahirrahmanirrahim. So first we'll try to discuss this pavement part. This is small part. So for pavement part, we have two different design methods. First is for flexible pavements, and the one is for rigid pavements. Both are from Astro, so we'll try to cover both of them today. So, and one thing is before that, we have this road node 31, uh, this road node design method. So this is quite simple. For in this design method, first what we have to do, we have to determine the ESAL, the equivalent single axle loads, just like we did that in the midterms. So for all that, we will determine this SAL's equivalent single axle loads. Using this equivalent single axle loads, we'll determine the class of the traffic. For example, if the ESL is 2 times 10 to the power 8, so our class would be between T4 class. So this is 10 raised to power 8. So whatever the traffic class is, we'll use this to determine, we'll use the ESL to determine the traffic class. And again, we'll use the CBR value of subgrid. The CBR value of subgrid would be given. We'll use it to determine the soil class. For example, our CBR is 6%. So our subgrade class would be S3. So T4 and S3. Just using these two tables, we can determine this T4 and S3. And if we move to these charts, so in this case, first we look at the S3 one. This is the S3 one, and this is a T4 one. So the pavement we should design would be something like this. Checkboards of 275 millimeters, then 200 millimeter this dotted ones, and 50 millimeter this which one?
Hamza,
Yes.
Hamza, along with your voice, some another noise coming. Means your voice is not clear now. Some background voice also coming, disturbing
Background
noise.
noise.
Yeah, yeah.
Okay.
Kind of echo.
Okay, one moment. So is the voice clear now?
No, Hamza.
No.
No, Hamza.
Now.
No, it's okay.
No, it's okay.
All right. So for this road node, so first of all, what we have to do, we have to determine the traffic class. So we can determine the traffic class simply from ESALs, equivalent single axle loads. So this value would be provided in the paper using this value and a subgrid CBR value. we can determine the traffic class and the subgrade strength class. And using this, if we move towards these charts, so for S3 class subgrade and T4 class traffic class, so we can determine whatever the type of a pavement would be. And for what these boxes and all this represent, so if we move to this legend, we can see that this checkboard represents this granular subbase, and it should be of 275 millimeters. Then this 200 millimeter is this one granular road base. So this would be of 200 millimeters, and the last one is our top wearing surface. So it should be double surface wearing. This means it should be double surface wearing. So that is using simply the traffic class and the subgrade strength class. We can determine this type of pavement what should we use, whatever its materials and whatever its thickness are. So this is all for road node. So any issue in this? To simply determine the traffic class and the subgrid class. Using that, we can determine using pavement using road node 31. Any issue in this one?
Brother, in this case, just we need to means calculate the thicknesses and write only that thing.
No need for that. We are provided the thicknesses like this. All thicknesses are provided. Just we have to know these two values, ESAL and this CBR of the subgrid. So these will be the CBR value will be provided obviously because we cannot conduct a test in the paper. But this ESAL value, it may or may not be provided because we know that 20% of the part may come from the mids. So sir may give this question like determine the ESAL value for some loadings. So just go through the mids part, the last example of the mids part, and for determine the ESAL. So, but most probably this would come in like quiz or something because this is not a major question. So any issue or should we move towards the main topics, these two ones, the flexible pavement and the rigid pavement from Extro.
Yes, Hamza will know.
All right. So for the flexible pavement, first we have the flexible pavement. If we directly move towards the numerical, we have this given ESAL value. So most probably ESAL value would be given in row 231 as well. So the given data is, if I write, this is flexible pavement. So our given data, first we should be given that what is our ESAL value? That is 2 into 10 raised to power 6, equivalent single axle load. And the drainage time is 1 week. So the second statement is drainage time is equal to 1 week. We'll use all this data to determine more values. The saturation level is 30%. Third thing is saturation is 30%. The fourth thing is the asphalt cement MR. MR is the modulus of resilience. So the MR value of asphalt cement. So MR of asphalt cement, that is equal to 450 100,000 psi. So this is our MR for asphalt cement. Our MR for sub base and our CBR. So this is all for if I write in the next page. So CBR for sub base 6 is CBR for base. The last is CBR for subgrid. So we'll be given all these values simply. Values are given as base course is 100, sub base is 22, and 6% is subgrid. Base is 100%, sub base is 22%. These three values are given. Sub base 22, base 100, and subgrid 6. And also we have provided that the road type is rural interstate. the reliability value and standard deviation. The reliability, and number 10 is standard deviation. The reliability is 99 and 0.49. 99% reliability and 0.49 standard deviation. And the last things are initial serviceability and final serviceability. So our initial PSI stand for present serviceability. So initial PSI present serviceability index is 4.5, PI is 4.5, and terminal or final is PET is 2.5. So this all values are given. This is all given data. The ESAL drainage saturation and MR for asphalt cement. The CBR value for sub-base, base and subgrade. The type of road. This is rural interstate. The reliability of road. The standard deviation and the initial and final uh, serviceabilities. So these all values are given. Any issue in this? This is all our given data. So for solution. So first of all, what we have to do, we have to find the delta PSI. That is simply the PI minus PT, the difference of these two initial and final values. So 4.5 minus 2.5, that gives us 2. So our delta PSI value would be 2. The second thing is we have to determine the MR values for this also, this CBR values. We have to convert this CBR values into MR values. We are known with the MR value of asphalt cement. But in this procedure, what we have to do, we have to find the MR values for each and every base and every quote. So we have to determine the MR values for all these CBR. So after finding the delta PSI, we should move to the charts, and here are the charts. So if we look here, so they say that the MR value for CBR less than 10, for the MR value of CBR less than 10 is simply 1500 times CBR. So whatever the for we have this subgrade as 6, it is less than 10. So MR value for subgrade would be 1500 times 6, that is 9000 PSI. Okay, if we have less than 10, so simply multiply it by 1500. So we'll get the MR, modulus of resilience, for this subgrade. Now for this base and subbase, for example, this chart is for subbase. They have written this as granular subbase material. So for subbase, we are known that our CBR value is 22. So if we move toward this chart, this is CBR. So at this point, this is approximately 22. This is approximately 20. If we move towards the right side, we'll get this modulus MR as 13.5, approximately between 14 and 13. So we'll write it as 13.5 raised to the power. This is in 1000 units, so it is raised to the power 3 PSI. Right, so simply using this sub base, we can write this MR value. And the last thing is for base. This is for base material, and our base CBR value is 100. If we move towards the right, we'll get this as 30,000. 30 days power 10, 3 PSI. Any issue in this? How we have to determine the MR values? First, calculate delta PSI. Second, move towards this and calculate the MR value for each and every layer. All right. So after this MR values, using these charts again, we can find this A coefficient. This A coefficient, where we'll use this A values. We'll see this afterwards. But now using these charts again for this sub-base material, we moved towards right to calculate the modulus of resilience. Now we'll move towards left to calculate this A coefficient value. So our for sub base we'll use this A3 value. For subbase, we'll call this as A3. For base, we'll call this as A2. And for this asphalt cement, we'll call this as A1. So asphalt cement as A1. If I draw this, so this is asphalt cement wearing core. Below this is base course, and below this is sub base. So this is basic structure of a pavement. So we'll call the thickness of our asphalt layer as D1, the base thickness as D2, and the sub base thickness as D3. So these are basic values. And simply we'll use the coefficient for asphalt cement as A1, base as A2, and sub base as A3. So we'll use these coefficients. So for first of all, we can calculate for sub base, that is approximately 0.1. Simply we can see this is 0.1. So our sub base would be 0.10. Now for our base, we had CBR of 100. If we move towards left, our coefficient would be A2 would be 0.14. And for our asphalt cement, if we move to the third chart, simply here this is 4 lakhs, this is 5 lakhs. So for 450, we can simply move towards the top to this curve and then simply move towards the left hand side. Just follow the chart arrows. So we'll get this like A1 value as 0.44, 0.45. Approximately they are same, so we can write this as 0.44, so we can verify our answer later on. Okay, so simply using these charts again, calculate the A values. Any issue in this?
No, brother.
Okay, so now if I look at this data, so we are given this drainage and we are given this saturation. We'll move towards the table, this one, and here it says that whatever the time is, accordingly we can determine whatever our drainage is. So if our time is 1 week, the time to drain the water from the layer is 1 week. That means our drainage is fair. So we can write this as if the time is 1 week, our drainage is fair. Our drainage is fair. So using this fair drainage and saturation as 30%, move toward this table. So our drainage is fair, this one, and our saturation is greater than 25%. Our saturation is 30%, if you remember. So greater than 35. So that means that MI value would be our 0.80. That means our MI value is 0.80. An issue in this that using drainage as 1 week, we determined that it is fair type of drainage, and from fair and saturation as 30%, we determined the MI value. So we'll MI value we'll use this onwards. So afterwards, we had this rural interstate reliability and standard deviation. So actually, this rural interstate means that this is actually if we are not provided with this reliability value. For example, in the paper, it is only written that the pavement is a rural estate and no reliability value is provided. So that means we have to assume reliability value ourselves. So for interstate and rural types, we can assume any value between 80 to 99.9. Actually, in this question, the reliability value is given, but if in the paper it is not given, we have to assume ourselves, and for assuming we must know the range. So we have to memorize this. That for interstate highways in rural areas, our reliability values lies between 80 to 99.9. Now in this question we are given, so there is no use for this thing. We are actually provided with the reliability value. So any issue up till this part? This is all the part. This is all the data we'll calculate from this uh, given data. Any issue up till this part?
Brother, to get these values, that we want to bring these tables, or if they're given this question, they will
They
provide.
would be provided. They would be provided at the back of the chart. At the back of the paper, this chart would be provided like before.
Okay, brother.
So if now after all this, now we have to move towards this flexible pavement design. So what we have to do, yes, this is a flexible pavement design. So if I rotate this, so if I rotate this page, for example, like this, so this is what we call as nomograph. This is a nomograph. So we'll use this nomograph to determine the structural numbers. So our basic design equation for this question is that we have this design equation as Sn1 that is equal to A1 D1, Sn2 that is equal to A1 D1 plus A2 D2 M2, and Sn3 has A1 D1 plus A2 D2 M2 plus A3 D3 M3. So these three equations you have to memorize. Sn stands for structural number. This indicates how much strong or safe our layer is. So more this value, the more strong our base is, our layer is. Sn1 determines stands for the is the structural number of the wearing surface or asphalt cement. The topmost layer, this is the asphalt cement. So if I move to this chart again, so this is Sn1. The first layer's coefficient structure number is Sn1. Sn2 is the second layer or the base layer. Sn3 is the third layer or sub base. So we have this Sn2 as like this, from Sn3 as like this. It is always up to the top and starting from that layer. So this is the structural numbers. So these are our basic design equation. If we recall, we have determined this A1, A1, A2, A1, A2, A3. Just before, just see this. A1 we have determined as 0.44. So A1 is 0.44. A2 we have determined as 0.10. So our A2 value is 0.10 and our A3 value is A2 value is 0.14 and A3 value is 0.10. A2 value is 0.14 and A3 value is 0.10. So that is why we determine these A values. So now I think that more clear why we determine the A values. So we determine the A values for this, for we have to put these values in these equations. So we also know this MI values, MI values. MI value means it is for sub base as well as for base. So both M values would be same. So our M2 for base would be also pointed. Our M3 for sub base would be also pointed. So that is why we determine these M values and A values. So any issue in this, these equations we have to memorize. Okay, so now if we look at these equations, first, if you look at this first equation, we have two unknowns, Sn1 and D1. So we'll determine this Sn1 from this nomograph, and using this Sn1, we'll determine this D1. This D1 is the depth of this topmost layer, the wearing surface layer. So first of all, if I write this equation as Sn1 as A1 D1. So we have A1 as 0.44, 0.44 D1, and Sn1 will be determined from this nomograph. So if we look at this, we have to start from the left hand side. First, if we look, this is they have given this reliability values. So our reliability value for this question is 99. So our reliability value is 99. So if you look at this portion, this is 99. So using this portion, this point 0.99, Now we'll look toward this standard deviation. So our standard deviation is 0.49. So point where is the 0.49 lies? This is zero point 0.4, this is 0.45, and 0.49 would be something like here. Fine. The standard deviation increases downwards. So now if we place a ruler here and join these two values, so will place a ruler and join these with a straight line. So we'll get this kind of line. So this is how we have joined the reliability and standard deviation values and moved toward this point. So afterwards, this EL stands for turning line. We'll reverse the direction of our this line. So we'll move now in the upward direction. So if we look at here, they say this is estimated total equivalent single axis load. So these are our ESAL values in millions. So our ESAL value would be here is 2 million, 2 into 10 days past 6. So where is the 2 value lying? So this is 1 and this is 2, I think. So now join these two again with this ruler. So these 2 points with a ruler. So if we join this with a ruler, it would be more accurate. So we'll move towards this point here. Okay. So now afterwards, we have this resilient modulus. So we are determining, first of all, we are doing this for the first layer. So the first layer, our resilient modulus we would use as this one. 13 into 10 raised to power 3. Remember, for the first layer, we'll use the resilient modulus of MR2. 2 means for base. For base, sorry. This was, I think, MR3. So this is MR3, sorry. We'll use for base, not this one. We'll use this one. So we'll use the MR value of the layer lying just below the required. What layer we are designing, we'll use the MR value of the layer just below it. So we will not use the MR value as 450 100,000. We are not going to use this. Although we are designing this first layer, this concrete layer, but we are not going to use this value. We are going to use the second layer value. The second layer is the base layer. The base layer we have as 30,000. So we are going to use MR value as 30,000. Okay. So 30,000. So 30,000 means this 30,000 PSI or 30 KSI. So here the units are KSI. So where is 30? The 20 is here and 30 is, I think, about here. So this is the 30 value. Now join these two again, these 2 points again. Okay, so this way we can get this kind of line. Any issue up till this part? Oops, sorry.
No, brother.
I think this whole got lost. So if I do this again, so 99% and 0.5, we are going to join this together, and using from here the turning line, we have this as 2 ESLs, 2 million ESLs. So we'll join this as like this, and from here our resilient modulus is 30 KSI. 30 is about here, so we are going to join this as like this, approximately this. So if you do this using a ruler, it would be more accurate. So now what we have to do, we have to simply move horizontally and check these curves. These curves are from delta PSI, what we calculated in the first step. So our delta PSI value was 2, 2. So just we are going to move to this 2 curve. This 2 curve is this one, I think. So they are approximately almost same here. So if we move towards this value and move downwards, our SN value would be approximately this. This is a bit before, so approximately 3.4. Is this fine? So our SN value, SN1 would be 3.4. Any issue up till this? How we are going to use this nomograph? First, we have reliability. Using that, we connect with the standard deviation. Then from turning line, we change the
Sir, I have
direction
a
of the
question.
line. Yes.
Why we are not using the modulus resilient for
Why we are not using the modulus revision of that layer?
yes,
Because this whole um the stability of this layer, this asphalt cement layer, it depends on what thing. It depends on how much stable is the below layer. For example, if the base layer is very much unstable and it has very depression like this, no matter how much we carefully place this concrete, of course it would develop many cracks. So the stability of the above layer lies on how much stable the below layer. That is why we are using the modulus of resilience of the below layer. Modulus of resilience means how much energy it can absorb before fracturing. So that is why we are using the below layer. The modulus of resilience of that layer does not depend. It has no effect on how much stable it will be.
thanks, got it.
Okay. All right.
Okay, okay.
So so using this equation, we can calculate d1 as 3.4 over 0.44. So that is approximately 3.4 divided by 0.44, 7.72. So this is 7.7 approximately. We can call this as 8 inches. So this is 8 inches. Now after rounding off, we'll calculate the structural number again, SN1, using exact values. So our A1 is 0.44 and our layer thickness is 8, and we can multiply it by, and we can get the value as 3.52. So the exact structure number is 3.52 for this portion. Okay, so for using the same method, we are going to use for the design the base layer. So our base layer is SN2, that is A1 D1 plus A2 D2 M2. Here SN2 we are going to get from the nomograph again, A1 D1. We know this A1 D1 as SN1. SN1 is A1 D1, and that is 3.52. So we can simply plug in the value as 3.52 of this whole. Now A2 we know as 0.14, 0.14. D2 we do not know, and M2 we know as 0.8. What we calculated using the drainage values. So using, now we have to determine the SN2 for the base layer. So if I remove this, now for the base layer again, our reliability value is 99. So this remains the same. Standard deviation value is 0.45 or 0.49. So this remains the same. So approximately this would be the same. Again, our standard axial loads are 2 million. So this remains the same. So up till this part, this chart would always remain the same for the same question, because we are having the same values. Now from this chart, due to different values of MR of different layers, we are going to get difference here. So for base layer, what we are going to use MR value, we are going to use MR value of sub base, the below layer. So MR value is 13,500. MR is 13.5 KSI. So for 13.5 KSI, so for this is 10, this is 15 approximately in between these two values. So if we connect these two values, oops, like this, something using scale, it would be more accurate. Move horizontally up till this two curve and then move downwards. So our structure number is 4 point, I think 4.4, I think. So we can write this structure number as 4.4. Fine. This is how we can get this SN value. We can write this structure number as 4.4. Actually, if we look at this SN1 should not be less than SN2. SN1 should have been greater than SN2. If we move towards this portion, and for 30,000 we have this one. If we move towards this, for the first chart, we should have a larger SN number. So that's approximately fine. So that's fine, I think. if we look at the solution, 1 minute. So our structure number at 1 should be lower or greater. Our SN1 is 2.6, SN2 is 3.8. So okay, that's fine. So our SN1 should be less than SN2. That's fine. So SN2 comes out to be 4.4. It is greater than SN1. That's okay. We are moving in the right direction. So now the only unknown is D2. If we solve this equation, we can find the value of D2. So 4.4 is equal to 3.52 plus 0.14x into zero point 0.8. If we solve this, we'll get the value as 7.8 inches. D2 is 7.9 inches, 7.85 approximately. So we can round this off to 8 inches. So our D2 value is 8 inches. Now exact SN2 number would be 3.52 plus 0.14 into 8 into zero point 0.8. Just plug in 8 in the place of D2, we can get the exact structural number. So we'll get this 4.416. 4.416. This is the exact structural number. When issuing this is exactly the same method as before, just we change the MR value here. So the last is SN3. So SN3 is A1 D1 plus A2 D2 M2 plus A3 D3 M3. So in this case, we know this whole expression. This whole expression is SN2. So we know this whole expression as 4.416. 4.416. Now we know this A3 as 0.1, I think, M2 as 0.8, and we don't know this D2. We can get this SN3 value from the graph. So our modulus of resilience is 9000 for the sub base. So the same point here, it will remain the same for the same question. So for 9000, it is approximately here. So if we move towards this and downwards, so we'll get this value as 4, SN as 4. So sorry, last one was not 4.4, it was 3.6. I thought there was some problem. Yes, this was 3.6. The value is increasing in this direction. So this was 3.6. Now this is 4. So just correct this value as 3.6. Now we have this value as 4. So plug in the values. 4 is equal to 4.416 plus zero point 0.1 D3 and 2.8. And this way we can get the D3 value. So this way we can design this pavement. So our pavement would be like this. This is asphalt cement. This is base. This is sub base. This thickness is approximately, we have something thickness. This is D1. This is D2. This is D3. So D1 we have as approximately 4 inches. D1 we have as 8 inches. D2 we have as 8 inches. Supposedly this we have it as 10 inches. So 8, 8, and 10. And this SN1 value is, we can write this SN1 value as 3.52, 4.416, and so on. 3.52. SN2 value as 4.416. You can correct this one as, and SN3 value as something. So this way we can design a flexible pavement through Astro method. Any issue in this?
No, brother.
Okay, so the last question for this part is the rigid design pavement. So if we move to this question also, so we have this ESAL rigid design, rigid pavement. What is rigid pavement? This ESAL value is 11 raised power 6. ESAL is equal to 11 into 10 raised power 6. Reliability 95, standard deviation 0.3. So we have reliability as 95%, standard deviation as 0.3. Initial and final at 4.5 and 2.5. Pi is 4.5, Pt is 2.5 initial and final submissibility, and delta psi would be 4.5 minus 2.5, and that would be 2. Other things are EC, the modulus of the Young's modulus for this concrete, that is 510 per 6. PSI, SC is 650 PSI, J is 3.2, CD1, J is 3.2, CD is equal to 1. So you can go through the values. J is something like joint coefficient, CD is drainage coefficient, SC is related to the modulus of resilience, and K is the modulus of subgrade direction, that is 72 PCI. So these all values are given. This is all given data. So what we are going to do, we are going to use the rigid pavement chart now. So if we move towards this portion, rigid pavement portion, yes. So this is a chart for the rigid pavement, this one. This is a nomograph for rigid pavement. So first of all, we start from the left again. First we have this K value. What is the K value we have in this question? We have this as 72 PCI. So we start from this 50 and 100. So approximately in the middle is 75. So approximately this is 75 value. So we move in this direction, 75. Now they are saying this the concrete elastic modulus, the Young modulus for concrete in 10 raised per 6 units. So that we have as the elastic modulus we have as 5. This one, 5 into 10 raised per 6. So we'll stop at the curve of 5. This is 3 curve, this is 4 curve, this is 5 curve. So after stopping at this curve, we'll move towards the right direction. Now, if we look, they are saying that this is the modulus of rupture. The modulus of rupture, that is SC. So the modulus of rupture is 650 psi. So we have this 650. The 500, 600. This is approximately 650. So we'll move in this, join these two portions with a straight ruler and move toward this turning line. Now this turning line, if you look, they're saying the joint load transfer coefficient. The load transfer coefficient at joint, that is, we have that as J value as 3.2. So now at 3.2, this is 3, this is 3.1, 2, 3, 4, 5. So approximately this is 3.2, this one. So we'll join this both lines with a ruler and exactly following the same example of Ashto. Oops. So we were at this point. So we were at this point. Now at this point, this drainage coefficient, that CD is value is 1. We have this value as 1. So for one value, this is 1.1, this is 0.9. So in between there is one value. So using this one value, we'll go to this, and approximately we are at 74 to 75. So we are at 74 approximately. So an issue in this homograph. 75 modulus subgrid move upwards, then rightwards. Now modulus of rupture is 650. So move downwards and join here. Now joint load transfer coefficient is 3.2. Join these two lines, and then CD's value is 1. So join these two lines and move towards this match line. This match line reads as 74. An issue up till this. No, so afterwards, using this match line, we'll move towards this chart. So this chart. So here we'll start from whatever the value of match line was in the previous one. So our suppose match line value was 74, the previous one. Now delta PSI. The delta PSI value is 2 in this case again. So for 2 value of delta PSI, just join these two lines, move here. Now we are at here at this point. So if I move towards downwards, if I zoom out a bit, so we were at this point. Stop at this point. Now start at the bottom. this reliability value. So we have this reliability value as 95% and standard deviation as 0.3. So 95% is our reliability, standard deviation is 0.3. Join these two values. Now we have this at this turning line. Now at this turning line, our ESCL, equivalent single axle loads, these are 11 in millions. So in millions we have ESCLs as 11. So approximately this is 5, this is 10. So approximately it would be something like here. So ESL 11 would be something like here. So we'll move towards this portion as like this. This is, I think, wrong. So if I draw a straight line, so approximately this line would be like this. We are moved at this point. So if I join this correctly, so we are at this point. So now just move the top line horizontally and the bottom line vertically. Where these two would meet, we'll get this thickness of concrete layer. So what we have to design, if we look here in this question, so we were following this question. No, I think yes, this one. So we were following this question. So they were saying to design a concrete pavement slab thickness. So the slab thickness would be, in this case, this this line shows the slab thickness. So our approximately slab thickness would be 11 inches. So we were our lines were meeting at this point, I think. So our slab thickness in inches is 11 inches. So we can simply write the inches D slab as 11 inches. So this is all this question. Any issue in this homograph, nomograph?
No, brother.
Okay, the second one is,
Brother, I have one question. While they are giving these graphs, that they will means name those graphs. It means like in here example, if that CD value, it was written CD value like that, or we should memorize it.
this thing. Yes, these would be given. Yes,
Okay,
these would
brother.
be given. Otherwise, we have to guess. No, I don't think they have to break paper would be that much hard. These would be given. So these are actually Astro guidelines, actual astrographs. So I've downloaded this book from Astro. So these are actually astrographs. So these must be provided. These are these are like some manual in PRC or Steel one. So the second part is we have to determine the composite modulus of subgrade direction. So if we look at this value, so if we look at this value, we were given here the K value as 72 psi. So what is K value? The K value we can call as modulus of subgrade reaction. So this modulus of subgrade reaction is very important in this rigid pavement design. We use quite a lot of we apply quite a lot of corrections on this. So after applying corrections, what we call this modulus as composite modulus. Composite modulus of subgrade reaction, or we can write as K value. So the corrected, the most corrected composite modulus we are going to use in this rigid pavement design. So actually in the previous question we were given this value K value. In actual conditions we have to find this K value ourselves. So first we have to find this K value, then we have to apply some correction on it, then we'll get this final K value, and we'll use this final K value, this composite K value in this question. So if we are not quite this K value in this question, we have to use the composite modulus value, and then we can design a concrete slab thickness. So now this is like this question, the second question is like a smaller part of question one. First we have to do the second question and find this corrected K value. Then using this corrected K value, we can move towards the first question and design the concrete slab pavement. If the K value was not given, if this K value was not provided. But actually this is provided, so we do not need to do. We are claiming this K value as most corrected value. So in the second question, they have saying that 6 inch is the base sub-base thickness. So problem number 2, the depth of sub-base is 6 inches. So 6 inches thick is the sub-base. Its elastic modulus is 20,000. Elastic modulus of sub-base, SP for sub-base, 20,000 psi. Resilience modulus is 7,000 MR is equal to 7,000 psi, and subgrade, and the depth of subgrade to the hard rock. So bedrock is lying at 5 feet below. For example, this is our road. This we have placed as subgrade. Sorry, this we have placed as subbase. This we have as base, and this we have as varying surface. So this is a road. So this straight line shows as subbase for the ground surface below the road. So this 5 feet shows as a bedrock, that hard strata is 5 feet below the subbase layer. So the top of the subbase layer to the hard rock, the length is 5 feet. So this all values are given. We have to determine K value composite. Okay, an issue in this given data. So these all values are given. Depth and most modulus velocity of subbase, modulus of reliance of subgrade, this is of subgrade, and lastly the distance from the top to the bedrock is 5 feet. So if no problems, then we can move towards again charts. So these charts are also provided in the slides, but in slides a lot of these are done, so they are confusing. So I'm using this Astro ones. They are much cleaner and more accurate, more visible. So this is the Astro one slide graph. So in this case, if you look, first of all, what we have to find. So first of all, for in this question, the procedure would be, first of all, we have to find the K at infinite depth. That we'll call this as K infinite. The second thing we have to find, that we have to correct this K value due to hard rock, the depth of hard rock. So we'll find this, correct this K value due to hard rock. So after correcting this, we'll get the composite, K composite. So this is actually the design methodology. So first, this graph is for, if you look at this graph, they are saying that semi-infinite subgrade depth. So this is K infinite. So this is this graph means that the hard rock is lying at infinite depth from the subgrade, tower subgrade. So first we have to find this K infinite. So if you look at this graph, so at the top we have this subbase elastic modulus ESB. At the bottom we have this modulus of resilience MR. So at the top we have this ESB, and at the bottom we have this MR values. Both values are given. At the x-axis we have this sub-base thickness. We have provided this sub-base thickness as 6 inches. So this is 6 inches. So these three values are given. So first of all, we'll start at this sub-base thickness. That's 6 inches. Now we'll move in the upward direction for sub-base elastic modulus. What was the value? It was 20,000. So we'll move in the upward direction and we'll move to the curve of 20,000. So if you look at, this is 15,000 curve, the above one is 30,000 curve. So there is no curve of 20,000. So we will approximate this value in the middle of these curves. So this is, we can say approximately this is 20,000, and we'll move horizontally and just we'll draw a straight line horizontally. Okay, so first we started at the sub-base thickness. We moved towards the curve of elastic modulus, sub-base elastic modulus, and then we draw a horizontal line at that point. Afterwards, we'll again start at this sub-base. Now we'll move downwards. We'll move downwards to MR value. Our MR value is 7,000 psi. So we'll move to the curve of 7,000. The curve of 7,000 is this one. So we'll move downwards to this curve. Then we'll draw a horizontal line to this turning line. So this turning line says that we'll shift the direction of this line. So we'll move vertically. So we'll draw a vertical line at that point. So where these two horizontal and vertical lines meet, we'll get this k value. So our k value on this curve is 400 pci. Okay, so this way we can get this k value. So our k value at infinite depth is 400 pci, pounds per cubic inch. So an issue in this: start at subbase thickness, move upward to the elastic modulus, and then draw a horizontal line from that. Now again start at subbase thickness, move downwards to the modulus of resilience, and then draw a horizontal line, and at the turning line, change that horizontal line to the vertical line. Where this vertical and the previous horizontal lines meet, that is the k value. If they meet in between the curves, we can approximate. Like if they were meeting at here point, suppose something at here, we can write this as k is 75. An issue in this infinite depth k.
No, brother.
Okay, so afterwards, now we have to apply this hard rock correction. So we are going to apply this correction on this k value. This k value was at infinite depth. Now we are going to apply a correction on this. So this is a correction graph. This is a correction graph. So now if we look at the horizontal line, horizontal axis, this is MR of the road base. So the road base MR value is 7,000. If we look at this, MR value is 7,000. So we'll start at this point. The MR value of this as 7,000, 5,000, 6,000, and 7,000. So we'll start at this point, 7,000. So at this 7,000, we'll move in the upward direction. So like this one. So our thickness from the bedrock was 5 feet. So we'll stop at the curve of 5 feet. So up till 10 feet thickness, we have to apply this correction. If the thickness of sub bedrock is greater than 10, if this is greater than 10, then no correction is applied. Then no correction is to be applied. Then there is no correction required. If the bedrock height is below 10 feet, then this value is our corrected value. But now because it is nearer to the subgrade, this is at 5 feet, so we have to apply correction. So we started at 7,000, move to upwards. So these curves are from subgrade to digit foundation. So we'll stop at the 5 feet curve because the distance is 5 feet. Now from here we'll move horizontally. So these curves, they show that semi-infinite subgrade. So they are actually k infinite curves. These curves are k infinite. So we had a k infinite of 400. If you recall, we have k infinite of 400. So we'll stop at 400 curve. This 400 curve, we stop at this one. So now we'll move downwards and we'll get this k as 500. So we'll k as 500 pci. So our k value increased from 400 to 500 due to applying this correction. So this is how we can get the modulus of subgrade reaction. This is how we can get the modified or composite modulus of subgrade reaction. This is the composite modulus of subgrade reaction, 500 PACI. So any issue in this part? First find the k infinite. Using that k infinite, find the case composite k. Actually, yes. One thing I forgot. We have to apply another correction on this. So after this if we have found this hard rock, then third correction we also have to apply of this one. If you look at this curves, so this relative damage correction, we also have to apply this one, the relative damage correction. So for this relative damage correction, if we move towards these curves, yes, this thing I think. So if they have said that to apply this correction, then we can apply, otherwise it is not required. Our question is finished at this one, that this is, we have this k composite, we have found this, but if they have written to apply relative damage correction also, so we have to apply this relative damage correction. So for this relative damage correction, for our x-axis we have this composite k value. What value we determined the previous step, the composite k value we are going to use now, this 500. So this is relative damage correction. So apply this if they have written to apply. So in the horizontal axis we have this relative damage. So sorry, so we have this composite k. So we have composite k of 500. So draw simply a vertical line. So now if you look at the slides, they say that if for interstate we have 9 inches thickness pavement, the PCC pavement would be 9 inches for interstate. I mean that for important routes, the thickness of the PCC would be 9 inches, and for the other roads it would be 8 inches. So these values are assumed. We are assuming this value. For example, we are assuming that this is an interstate road. So first we can draw a straight line from 500 because our composite K was 500. Move towards 9-inch curve. This is 9-inch curve. Sorry, this one is 9-inch curve. So this one is 9-inch curve. So now move horizontally and we can get this relative damage as 0.6. So U value as 0.6. So we can get U value as 0.6. So if we multiply this K with U, that means 500 into 0.6, we'll get this corrected K value. So it will be like 500 into 0.6, 300 PCI. So actual K value corrected is 300. But only do this step if they have required, if they have told in the question. Otherwise, the question was finished up till that part, that uh, this part, that we have determined the composite subgrid modulus section. So 500 is a composite. That's finished. But if they have told us to do this relative damage correction as well, so we have to do this one. That is why I have explained this one. So any issue in this?
No, but
All right. So the last one is this. Last one is again the same question. Just we have to do this for 12 months. So this we have to do this for the whole year. So for this purpose, we have to draw a table. Astro has provided us a table as well. So we have to draw this table. So for month, we have to do this modulus MR value for subgrade. For subbase ESB for composite value, we'll calculate from the chart like before. So if I draw a table, first we have months. So January, February, March, April, May, June, and so on. Afterwards, we have months. We have this modulus of resilience of subbase. So modulus of resilience of subbase would change in each month. So this depends upon the temperature. So the modulus of this resilience would change at each month. So these values would change each month. These values would change. Again, the ESB values, the elasticity of subbase. The modulus of resilience, remember it was a subgrade. The elasticity is of subbase. The subbase values would also change with each month. So these are all changing with each month. So whatever the values is are, first we have to find the K composite. So again the same procedure we have to apply, just we have to apply this 12 times. That for each month our MR and ESP values are given. So for each month, if MR and ESP values are given, and subbase base thickness is also given, it is given in the question as, okay, so it would be provided in the question. So our subbase thickness is given, ESP values are given, and MR values are given. So we are going to use this whole procedure for 12 times. We have to apply this whole procedure 12 times and get K value. for each month, k infinite value for each month, and we have to correct this k infinite value for this height below the height of hard bed below the subgrade. So this is how we can. So all the what I meant to say is all the procedure we applied in the previous question, we applied this one time that we found the k infinite, and using that k infinite we found the k composite. So apply this whole procedure each month for 12 times. So we'll get this k composite values. So in the question they have directly provided us the k composite values. The composite k values are given as 145, 145, 160. If they are not given, then we have to do for each month on the same basis like before, 180 and so on. So each month they have already provided us the k composite values. Now after these composite values, if you look at this table, what is next? This is k value on rigid foundation. That k value on rigid foundation that we corrected on the rigid foundation. So these are correct. If we look at this question, so there is no mention of correction, that there is no hard rock. They have no mention. They haven't mentioned any correction. The hard rock something data. So we'll assume this k composite as k hard rock. That there is no correction applied. So this was actually k composite. They and then applying correction of hard rock. Actually, this is, if it is more clearer, we can write this as k infinite, and this was first column was this k infinite, then the second column this is k hard rock is actually the k composite. So this is the k composite after applying the hard rock correction. So this is k composite. Fine. So this is how we can get the k hard rock. So if they have not mentioned those, we can assume the same values. So these are all the same. So the last column we have is the relative damage values. So this we have to keep in mind. So if I remove this, because these two columns are same, so the relative damage. So how we are going to we are going to find the relative damage? Again the same procedure. Move to this chart. They have told us to assume thickness of concrete as 9 inches and LS value as 1. So for 9 inches pavement, so we have this 9 inches pavement. This is the 9 inches pavement, and this is a 9 inches pavement, and this is value of subgrade was I think 145. So we can write this as 150. So approximately here. So for 150 and that we can get this value as approximately 90. So our correction would be 0.9 times 140. So we can write this as simply 0.9. Similarly, this would also be 0.9. At 160, it would be a bit more. So we can write this as 0.92. 0.92. This we can write as 180. We can write it as 0.95, I think. So these are very closer to each values. Very close values. So this way we can get the relative damage for each layer and issue up till this part of table. So this is actually table is all the same question. Just we have to do is this one as in 12 intervals, or we have to do this 12 times and issue up till this part. No. So what we have to do after finding all the relative damages, we have to sum these relative damage, that we have to sum this, and whatever sum is we have to divide it by number of months. So the number of months or number of intervals we have as 12. So if we have more intervals like 1 week interval, we can divide by 52, or whatever the number of intervals are. We have to find the average UR, that is a sum over number of intervals. So using this average UR, for example, if we got this average UR as I some value, like if we look to the slides, So if we get this average UR value is 0.6. So the summation was 7.25 divided by 12, that is 0.6. The average UR value is 0.6. So now we are going to do the opposite method. That for 0.6, we are going to start from 0.61, move towards 9-inch thickness. So this is 9-inch and move downwards. So this is approximately they are written 540. So our K effective value, this we call as effective value as 540 PCI. So the U average was 0.6. Now we moved, first we moved from down to the right. Now we started from the top and moved downwards. So we know this K U value, we started to the right and downwards moved. So we'll get this K effective value as 540. Now, so the last correction on this one is this correction for effective subgrade modulus. The correction is potential loss of support. The loss of support, the LS value, loss of support. The LS value is given as 1.0. So for 540, this is 540. Move towards the top. For the LS1 line, stop at the LS1 line. So for example, this is our LS1 line. So now what we have to do, so no, sorry, this is not 540. This is 100, this is 200, 300, 400. This is 500, I think. So this is 540. So we move towards top, and this, yes, this point, this is for LS1 line, and we move horizontally. So we'll get the K corrected as 170 PCI after loss of support. The loss of support, after loss of support, we'll get this KC as 170. So any issue up till this part. This is all about pavement design. And there are some 2-3 small things like this. If you look at this question, that this formula, this is 7. So CL and all these are mentioned below. The CL is the adjustment factor. This we have to use 0.6 or 0.8 simply. The L is the length of the joint spacing. Would they are to be provided. The alpha C is the coefficient that you can see in this table for alpha C. And dt is the temperature range. So the final temperature minus initial temperature, we can get the temperature in Fahrenheit. The Z is the drying shrinkage coefficient. This we can also get from this table. So all these values we can get from this table, and S is the strain allowed. So this is all these values are given. 25% we can use a conservative. Simply multiply and get the delta L value, the joint sealant value. So simply this is all simple numerical. Only values we have to plug in and place. And the last thing, these two things, uh, this one. This one is the this is the chart for reinforcement. That how much is the raw value of this concrete design we are going to check. So the raw value we can get from this chart. So for example, in this example, they are given the length as 35, F as friction factor as 1.5, and F as the uh, what we can say elastic stretch limit of steel as 330 ksi. First we have to do the 35 psi length, friction factor is 1.5. Simply draw this line. Now turn this line, and we have this steel stress as 30,000 ksi. So join this point by this point. Wherever this is matching, read the row value from here. This is the row value. So we can get the row value like this. And the last, this friction factor and working stress tables are given. They would be provided in the paper, I think. Or we can get like some hint will provide us the cement stabilization is used. So we can use the friction factor for that as 1.8. Some hint will be provided in the question. In the tables are also provided. And the last thing is transverse tie bars. This table is for grade 40. and the previous table is for sorry, this is for number 5 bars, 5 over 8 inches, and this is for number 4 bars, 4 over 8 inches or half die bars. So for this question, we are given the distance from free edge and the depth. So what we can do is simply distance, use the distance, move towards the top, the depth of the slab, the slab depth, and move towards left and get this minimum spacing. And similarly for grade for 5-inch dia, the same procedure applied, just the spacing value would increase because we are using a die of greater bar. So this way, this is all for pavement design. Any issue in this part?
No, Hamza.
Okay, so if I stop the recording here.